Hello everyone. In today's lecture, we are going to learn about how to design a 4-bit adder and subtractor composite unit. Now, for this, we are going to use the IC7483, that is the 4-bit adder IC, and the IC7486, which is basically a XOR IC containing 4 XOR gate. In this video, we are going to cover the full adder, IC7483, which is a 4-bit adder, IC7486, which is logical XOR gate, and working principle of this composite unit. Then we are going to discuss about the circuit design, and finally we are going to discuss about the result we are getting. Full adder takes 3 input, single bit input, and perform the addition, binary addition. So what are the 3 input? The one input is A, another is B, and another one is C in. C in stands for carry in. Suppose we are considering that if there is a carry from the previous bit, then that carry in will be 1. If there is no carry, then the carry in will be 0. So a summation, the output summation of a full adder can be given by this equation: A XOR B XOR C in. So this is the summation, and the carry of a full adder will be generated when at least 2 input is 1. So it can be either A and B, it can be either A and C in, it can be either B and C in. So if A and B or B or C, B and C in, or A and C in, one of them is true, then the carry will be generated, and you can verify from this truth table. So this is the full adder truth table and how to calculate the sum and carry for a full adder. Now, next we are going to discuss about the IC7483. IC7483 is a 16-pin chip, and it mainly takes 2 4-bit binary number as an input. Let us say one input is A and another one is B. So it takes 4 input, means the bits are A3, A2, A1 and A0, and B3, B2, B1 and B0. These are the 2 input consisting of 4-bit each. Now 4-bit input means the value of A can range from 0 to decimal 15. Similarly, the B is range also from 0 to 15. So it can perform addition of any decimal number from 0 to 15. Now, performing that addition, it will generate a 4-bit result for sum. So sum will be a 4-bit result consisting of S3, S2, S1 and S0. And it will generate a single bit carry, that is C out. So the carry will be generated when the result couldn't be held in 4-bit. Means if the sum or the result is greater than 15, that time carry will be generated. And if the result is less than 15, then there will be no carry, means carry bit will be 0. Now, what about the carry in? Carry in is given at the pin number 13 in diagram of this IC7483. You can see that the carry input is at pin number 13. Now, this carry in will be used for designing adder which is more than 4-bit. So if I am using IC7483 and designing a 8-bit adder, that time this carry in will play an important role. Otherwise, if I concentrate on the 4-bit adder only, then the carry in will be 0, right? So the final result, that is the summation, will be actually A plus B plus C in, right? This is the pin diagram of IC7483. You can see that there are 4-bit input A and there are 4-bit input B. Now, performing the addition of A and B, it will generate a 4-bit output, that is the sum, and it will generate a carry at pin number 14. Now, the input carry will be taken at pin number 13, and its ground is VCC are in 5, and ground is in pin number 12. So this is the pin diagram of IC7483. So the input will be connected at pin number 1, 3, 8 and 10 for A, and for B the input will be connected at pin number 16, pin number 4, pin number 7 and pin number 11. B3, B2, B1 and B0 respectively. Now the carry will be generated at pin number 14 and the summation will be generated at pin number 15, pin number 2, pin number 6 and pin number 9, S3, S2, S1 and S0 respectively. Now for the carry input, the pin number 13 is used to get the carry input. If we are concentrating only for 4-bit adder, then the carry input will be 0. And if we are considering more than 4-bit adder, then the carry input will be the carry out of the previous 7483. Now ground is at pin number 12 and VCC at pin number 5. So this is the pin diagram of 7483. Next, we are going to discuss how the 7483 actually perform in tasks. 7483 actually uses 4 full bit adder within it. So this is the internal circuit of a IC7483, and you can see that there are 4 full adders. Now the first full adder will perform the addition of first bit of A and B, that is A0 and B0, and this carry in will be added to the first bit, right? So we can say that A plus B0 plus C in. Now if and the summation will give it S0 and the carry out will be used in the next full adder C in. Let us take the C out. We are using the name C1. So the next full adder is actually performing A1 plus B1 plus C1. C1 is coming from the carry of the previous addition and previous full adder addition. Now it generates a summation S1 and the carry out. The carry out we are considering the name is C2. Now this C2 will be the carry in for the next full adder, that is the full adder number 3. So the full adder number 3 is performing A2 plus B2 plus C2, right? Now A2 plus B2 plus C2 will generate my third bit of the sum, that is the S2, and it will generate the carry. Let us take the name is C3. Let us take the name is C3. So C3 will be carry in for the fourth full adder, and the fourth full adder will perform A3 plus B3 plus C3. Finally, the fourth bit or the most significant bit of the sum, that is S3, will be generated, and here the carry is my final carry. So let us take some example and see how the IC7483 perform its tasks. So now let us take, we are performing 10 decimal 10 plus decimal 2. So A is 1010 and B is 0010. Now we are considering there is no carry, so carry is 0. So the result will be 0, 0, 1, 1, and carry out will be 0. So its binary representation is, decimal interpretation is 12. And remember, we are actually performing A plus B plus C in. So in other words, I can say that we are performing 10 plus 12 plus C in is 0, so 0, and it will be, the result will be 12. Now suppose here we are considering I have a carry in. Now in general, if you are using only 4-bit adder, the carry in will be logic 0. If you are designing a multi-bit adder, more than 4-bit adder, then the carry 1 carry in will come from the previous bit addition. So we are performing 10 plus 2 plus here we are considering the C in is 1. So the final result will be 1, 0, 1, 1 and carry out will be 0. So the decimal interpretation is 13. Now suppose we are going to perform addition of 11 and 7. So 11 is given by 1, 0, 1, 1 and 7 is given by 0, 111. Now consider carry in is 0. So from directly decimal addition we can say that the result will be 18 and we know that 18 cannot be contained within 4-bit binary representation. We need at least 5-bit binary representation. From this understanding, we can say that if this addition will generate a carry at Cout. Now, if we perform the binary addition, the result will be 0, 1, 0, 0, and the carry out will be 1. Now, if this sum will give me 2, and if we consider the carry out for decimal interpretation, the carry out is 16, so it is 16 plus 2, that is 18. By positional value, it is 0, it is 1, 2, 4, 8, then it will be 16. So 16 plus 2, it is 18. Now, similarly, if we perform 8 plus 9, and here we are going to consider there is a carry. So 8, A is 8 in binary, it will be 1, 000, and 9, it will be 1, 0, 0, 1. Now we are considering if there is a carry 1, carry in, and the result will be 0, 1, 0, 0, 1. So the decimal interpretation will be same as the previous, that is 18. Now for better understanding of the binary addition, you can follow my video lecture on number system. The link is given in the description. There are 4 XOR gates are available. Remember, this is a 14-pin chip where the ground is at pin number 7 and pin number 14 is for VCC. We have 4 XOR gate in it. Now, what is the purpose of the XOR gate is, as we know that if we fix input of a XOR gate to 1, the other input will be complemented in output. So if this input is fixed to 1, if the other input is x, then the output will be x complement. Similarly, if input is fixed to 0, that is ground, logical 0, and in that case the other input will be carried to the output as it is. So if, in other word, I can say that if we fixed input to logic 1, and in that case the other input will be inverted. So XOR will now act as a NOT gate. Now if one input is fixed to 0, that is the logical 0 or ground, the other input will be carried out to the output as it is. So it acts like a buffer. Using this property, we are going to design our adder subtractor composite circuit. Remember, IC 7483 is just a 4-bit adder. It cannot perform the subtraction by itself. So for subtraction, we need to design the circuit. To learn more about the logical gates, you can follow my video. The link is given in the description. Let us discuss the working principle of the circuit we are going to design. For addition purpose, we are going to use the simply binary addition, and for subtraction, we are going to use the 2's complement subtraction. To know more about the 2's complement subtraction, 1's complement subtraction, conversion from binary number to is 1's complement and 2's complement, you can follow my video lectures, which the link is given in the description. Now here IC7483, the pin number 13, that is the C in, is used to decide the operation. Operation means either it will perform addition or it will perform subtraction. The pin number 13, that is the C in, will decide that operation. Now, if we are going to perform addition, the C in will be set to logic 0. If we are going to perform the subtraction, the C in will be set to logic 1. Now, the in case of subtraction, the the IC7486, that is the logic XOR gate, will generate the ones complement of the input B. Now let us go to the circuit diagram and see how the circuit is designed. So this is the circuit diagram. So you can see that pin number 13 is connected to the one pin of each of the XOR gate in IC7486. So this is basically the IC7486. Now, what is happening? The input A is directly going to the IC7483, that is the 4-bit adder, and the input B is coming through the IC7486, that is the XOR gate. Now, and C in, that is the carry in of IC7483, is connected to each pin of the one pin of the 4 XOR gate available in IC7486. Now let us understand this configuration, why it is needed. So this is my configuration. You can see that the B3, B2, B1 and B0, the B out input of IC7483 is coming through the XOR gate, that is IC7486. Now C in is connected to one of the input of each of the 4 XOR gate. So they are shorted. Now if I give C in equals to 0, then here I am making it 0, 0, 0 and 0. So as we have discussed earlier, if we fixed input of a XOR gate to logic 0 or ground, then the output of this XOR gate will be same as the other input. In this case, it is B0. It acts like a buffer in this case. So in this case, it is fixed to 0, so the output will be B1 depending on the value of B1. It is fixed to 0, so the output of the XOR gate will be B2, and in this case, it is B3, right? So now let us take an example and see how the circuit is going to perform. So we are performing 10 plus 2. Now, as we know that C in will be decide the operation, so we are performing addition, so C in will be at logic 0. Now from the circuit diagram, we can see that A is going directly to the 7483. So directly going to the 7483. So the binary input here, A is 1010 and B is 0010. Now A is going directly to the 7483, so I can write here A is 1010 and A is, and for 7486 there is no need to write anything, and C in is not concerned about 7483. Now B is going to 7486, and let us take how it is working. So if we zoom into the XOR part, here my C in is 0, so I will put 0, 0, 0 and 0 over here. Now B3 is 0, B2 is 0, B1 is 1, and B0 is 0. So this is my XOR gate configuration right now. As we know that the XOR gate, if input is fixed to 0, the other input will be carried to the output directly. So XOR gate acts like a buffer. So the output of the XOR gate will be 0, 1, 0, 0, right? So if I put that into the table, so B is 0, 0, 1, 0. That is the output of the XOR gate. Now that output of the XOR gate is going to the B input of the 7483. That is B. This is my B3, B2, B1, and B0 of 7483. So 7483 B is having the value 0, 0, 1, 0, and carry in is 0. Now, if we perform the binary addition, the result will be 0, 0, 1, 1, and carry out will be 0. So finally, we can say that here we are giving 0, 0, 1, 0. C in is 0. So here I am giving 0, 0, 0, 0. So I will get 0, 0, 1, 0, and A is 1, 0, 1, 0, and the result is 1, carry out will be 0. So this is my configuration for 10 plus 2. Now let us put that into the table. So here it is 10, it is 2, operation is addition. As addition, carry in will be 0, so binary representation is 1010, and B is 0010. The result will be 0011 with the carry out 0, and its decimal representation is 12. Now let us take another example. Suppose we are performing 9 plus 10. So if we perform 9 plus 10, so binary representation is 9 of A is 1001 and 10 is 1010. As we are performing addition, C1 will be 0. Now A is not coming through 7486, but B is coming through 7486. Now go back to this one. Now here the C in is 0. It will be 0, 0, 0, 0, and B3 is 1, B2 is 0, B1 is 1, and B0 is 0. So the XOR gates will act like a buffer, and we are getting 1, 0, 1, 0. So we are performing 9 plus 10. A is 1, 0, 0, 1, and here we put all the values. So the input of 7483 is this, and the final result will be summation will be 1, 1, 0, 0, and a carry will be generated. So the result will be 1, 1, 0, 0, and a carry will be generated. So let us put that into the table. So we are performing 9 plus 10. Here addition, so Cin will be 0. So A is 1001, B is 1010. Now the result is 1, 1, 0, 0, 1. So its decimal interpretation will be 19. Now let us take an example where we are going to perform subtraction. Let us take, we are performing 10 minus 4. So as we are performing subtraction, C in obviously will be 1. B is 0, 1, 0, 0. And A is 10, so it will be 1, 0, 1, 0. Now, A is not coming through the 7486, so it will be nothing, and Cin it will not depend on 7486. Now let us come to 7486 part. Cin is equals to 1, so this one input will only be 1, and B is 4, so it will be 0, 1, 0, 0. So this is my B27486. Now, as we know that if one input of the XOR gate is 1, the other input will be complemented. So it will give me 1, 0, 1, 1. You can see that the XOR is generating the ones complement of the B input. So let us put that into that table. So I will get 1, 0, 1, 1. Now that input, the output of 7486 will be go to the input. So I will get 1010 and B is 1011 and Cin is 1. So put that into this one. So we are performing 10 minus 4. Cin is 1. So 1, 1, 1, 1. And B is 0, 1, 0, 0. So the input to the 7483 for B, it is 1, 0, 1, 1. And A, it is 1, 0, 1, 0. Now, here we are actually performing A plus B plus C in. Now, here B is one's complement of the actual B. We have already discussed that XOR gate is doing the ones complement of B. Now ones complement and C in here is 1. So ones complement of B plus C in is the two's complement of B. We are actually performing A plus ones complement of B plus C in, which value is equals to 1. Now, as Cin is 1, so I can write that A plus 2's complement of B and any number plus 2's complement of the other number, 2's complement subtraction. So we are performing A minus B in 2's complement. And if we perform this 2's complement subtraction, we will get the result 0, 1, 1, 0 with the carry 1. So the final result will be 0, 1, 1, 0 with the carry 1. Now, for better understanding of the 2's complement subtraction or binary subtraction or 1's complement subtraction, you can follow my video given in the link is given in the description. Now we know that in case of 2's complement subtraction, if the carry is generated, then the result will be a positive one and the carry will be discarded, right? To interpret in its decimal value. So we are performing 10 minus 4. Here Cin will be 1 as the subtraction, the process is subtraction. So 10 is 1010 and 4 is 0100. Now we know that the result is 0110 with the carry 1. Now for decimal interpretation, the result is positive and the carry will be discarded. So finally we get, so the result will be interpreted as plus 6, which is a correct result. Now let us take another example where we are going to get a negative result. So we are performing 4 minus 10. So A is 4, so 0, 1, 0, 0. Cin is 1 as we are performing subtraction. B is 1, 0, 1, 0. So output of 7486, the B will be once complemented. So 1, 0, 1, 0. Now input to 7483, it is 0, 1, 0, 0, and B is 1, 0, 1, 0, 1, and C in is 1. We are performing A plus B plus C in. Now in 7483, now B is 1's complemented form. So we are actually performing 1 plus 1's complement of B plus 1, that is A plus 2's complement of B. So that is A minus B in 2's complement subtraction. So if we perform the operation, the result will be 0, 1, 0, 1 with the carry output 0. Now in 2's complement subtraction, we know that if the carry output is 0, then the actual result is a negative number. So its decimal interpretation will be, it will be a negative number, and the actual result is the 2's complement of the result we are getting. So if we perform the 2's complement of this one, then the result will be 0, 1, 1, 0, and it will be a negative number. So we can say that the result is a minus 6, right? Now, so let us put that here. So subtraction, it will be 1, 0, 1, 0, 0, and so minus 6. Now, so how this circuit is performing? The circuit is performing in this manner: 0, 1, 0, 0. B is 1, 0, 1, 1, 0. B is 1, 0, 1, 0. Carry in is 1. C in is 1. So C in is 1. So it will be 1, 1, 1, 1, and we get the complemented form, 1's complement form of B. So it will be 0, 1, 0, 1. So this plus carry in will give me the result 0, 1, 0, 1 with the carry output 0. So the result will be a negative number, and the final value is the 2's complement of the result we are getting. So this is for 4 minus 10. So let us take another example. Suppose we are performing 10 minus 10. So A is 1010, B is 1010, and C in will be 1, as we are performing minus. So we'll get the 1's complement of B by 7486. Then we are going to add this value of A with value of B plus C in. So we will get 0, 0, 0, 0, and carry out will be 1. As carry out is 1, we know that the result is a positive number and its value is 0. Its value is 0. So that is how the circuit is performing. So let us put that into that circuit. So 10 minus 10. So 10 minus 10 we are performing. So A is 1010, B is 1010, C in is 1. So 1, 1, 1, 1. So output of this one will be 0, 1, 0, 1. Then A plus B is 1's complement plus C in, and we'll get the final result 0, 0, 0, 0 with the carry out 1. So that is how the how we can design a 4-bit adder subtractor composite unit using IC 7483 and IC 7486. So that's it for today's video, and see you in the next video where we are going to discuss about designing a BCD adder.